Hello, thank you for joining me in the PBM and Tinnitus Lab channel. I'm Dr. Katoyun and this is the second session of the Tinnitus series. In this video, I'm going to talk about the brain changes in tinnitus. These changes are very important because they play an important role in the development, persistence, and also annoyance of tinnitus. In most of the tinnitus cases, there is a cochlear damage, and in the first session of tinnitus series, I explained the causes of cochlear damage, and you can watch it if you want to learn it. The damaged hair cells in the cochlea either stop sending the right signals to the brain or started to send random and spontaneous signals to the brain. So in general, this leads to a decrease in the auditory input to the brain, and brain always tries to keep its balance, and it tries to fill in the gaps. To make up the decrease in auditory input, brain tries to ramping up its activities or change its activities. So the brain doesn't stay idle and always try to adapt to the changes, and in the condition of loss of auditory input, the changes in brain include remapping auditory areas, which is a kind of plasticity, and I've explained it. Amplifying the internal signals due to hypersensitivity in the auditory cortex, which in response to a loss of input, and is also called as increasing central gain, generating abnormal brain rhythms or dysrhythmia, engaging emotional and attentional circuits related to the limbic system and also prefrontal cortex, and adapting through inhibition and habituation. These changes allow brain to maintain its important function even when there is a damage in the part of the system. But sometimes these central compensatory changes leads to a perception of a phantom sound. So even though there is no sound exists, the brain behaves as if there's a sound, and this is the beginning of tinnitus. The ways that the brain uses to create to maintain its balance, categorized into three main topics. Changes in brain neural oscillations, changes in tonotopic map which is related to the sound frequency, and neural plastic changes. Each of these changes are related to the others, and I will explain all of them. Neural plasticity refers to brain's ability to adapt structurally and functionally. Brain tries to keep its balance through some adaptation and some changes, and these changes are reorganized in the case of auditory input, loss of auditory input. These changes are a reorganization of cortical space for better representing the useful frequencies. The rule fire together, wire together, which helps strengthening connections of coactive neurons, also called as Hebbian plasticity, and the neurons taking over space from inactive neighbors. It means that the active neurons invade to the inactive spaces. For example, I will talk about, at first I will talk about the brain tonotopic map. This is the schematic illustration of the auditory cortex, and consists of primary and secondary auditory cortex. And the auditory cortex is tonotopically organized according to the frequency of sound from low to high. It means that each sound frequency has its own and its specific space in the auditory cortex, which helps brain to interpret the sound frequencies accurately. And in the some conditions like loss of auditory input, there will be a reorganization of this tonotopic map. This is a schematic illustration of reorganization of tonotopic map. Auditory cortex no longer receives input from certain frequencies, and the adjacent neurons may invade to the deprived area, and these invaded neurons start firing spontaneously and synchronously, which may perceive as a phantom sound or tinnitus. Now let's have a look at the important role of thalamus. Thalamus is very important in the perception of tinnitus, and thalamus is a deep brain structure, and it's like a relay station in brain. It means that it receives the sense of different senses and for example somatosensory or another inputs from different senses, and relay these inputs to the auditory cortex, to the appropriate part of auditory cortex. And in the case of loss of input, the balance of neural activity between thalamus and auditory cortex can be disrupted, and leads to the abnormal oscillatory activity. And now let's have a look at the brain neural oscillations. These are the rhythmic or repetitive patterns of neural activity, and they helps in keeping the brain balance and the balance in the brain, and also they helps in communicating the different parts of the brain, different regions, and they process, and they help in processing the information from the different areas of brain. So each band of frequency of these neural oscillations is related to a specific brain state. Delta waves are from 0.5 to 4 Hertz frequency, and they are related to sleep and deep rest. Theta waves are from 4 to 8 Hertz frequency, and they're related to memory processing and drowsiness. And alpha wave are from 8 to 13 Hertz frequency, and they're related to rest and sensory inhibition during the during the rest. And beta waves are from 13 to 30 hertz frequency, and they are showing up in active um, thinking and focus. And gamma waves are from 30 to 100 hertz frequency and are related, contributed to perception and consciousness. These neural oscillations are very important in maintaining the balance in brain, and they are very important in the perception of tinnitus. Brain has the ability to change these oscillations to keep its balance. So the changes that brain create in these neural oscillations include, for example, I'm sorry, the brain can adjust these oscillations in terms of their frequency and amplitude, and the excitatory and inhibitory neurochemicals in brain can modulate these oscillations. It means that the neurotransmitters like GABA or gamma aminobutyric acid, which is an inhibitory neurotransmitter, and glutamate, which is an excitatory neurotransmitter, can modulate these neural oscillations. And also the oscillatory power can shift to adjacent area, like the reorganization of tonotopic map, which is a kind of a compensatory plasticity. These neural oscillations are changed in tinnitus, and the amplitude of delta, beta, and gamma waves is increased, and the amplitude of alpha waves is reduced in tinnitus. So these changes can lead to a persistent signal which interpret as sound, as tinnitus sound. One of the plasticities that can happen in tinnitus is cross-modal plasticity. It means that the somatosensory inputs can invade to the auditory pathway, and so the other senses, the input of other senses can invade to the auditory system, and this cross-modal plasticity can explain the reason of why some patients can modulate their or change their tinnitus sound by moving their, for example, head or neck or jaw. And this cross-modal plasticity, which show the connection between the somatosensory senses and auditory inputs, is very reinforcing in tinnitus and make it more complex. Tinnitus isn't just an auditory perception, and it involves the other parts of brain. Involvement of, for example, prefrontal cortex and also the limbic system are confirmed in tinnitus, and these areas handle the emotion, attention, and memory, and they are involved in tinnitus and make tinnitus more distressing and harder to ignore. And thalamus, which is the relay station of brain, connects sensory inputs with the emotional processing area, and it has plays an important role in the distress and the disturbing feeling in the tinnitus. So if I want to review what I said and how tinnitus occurs, at first it's loss of auditory input leads to a maladaptive neural plasticity in brain, and then leads to the perception of a phantom sound or tinnitus. I'm very thankful from the scientists that I used their findings and the findings of their research in this presentation, and I pay tribute to all of them. Thanks for your attention. If this video was useful for you, please suggest it to your friends and to the tinnitus patients or researchers, and please subscribe the channel. My next video will be about the modulating effects of transcranial PBM on the brain. So stay tuned and have a nice time.